Hi, I'm Yan Yang from the Australia National University. Today I will talk about disparity over kernel estimation for dual pixel defocus deblurring. The work is done with Li Yuanpan, Liu Liu, and Miao Miao Liu. In this work, a disparity over kernel estimation for dual pixel image pair defocus deblurring network, namely K3DN, is proposed. Given a defocus blurred dual pixel image pair, we aim to restore the defocused region by a disparity over deblur module. Meanwhile, the sharp region of the dual pixel image pair is preserved by a sharp region preservation module to improve the restoration quality. Before jumping into our model component details, we briefly review what is defocus blur and how it is related to the dual pixel image pair. In a modern camera, different sizes of apertures essentially correspond with different depths of field. A wider aperture can capture more light from the scene while producing less noisy image. However, a wider aperture leads to a shallow depth of field, potentially resulting in a defocus blurred image from the scene with a large depth of field. For example, supposing the background of the scene is outside of the depth of field of the wider aperture, and the foreground is within the depth of field. Then, in the image, we will have a focused foreground and a defocused background. The amount of defocus blur is spatially varying per the background depth. One solution to avoid the image defocus blur is using a shallow aperture that has a higher range of depth of field. This will lead to an all-in-focus image. The defocus blur behaves similar in the dual pixel sensor, which is designed by Canon. In a dual pixel sensor, each px is divided into two photodiodes to provide two sub-views of the scene, namely left view and right view. For an all-in-focus dual pixel image pair, the left and right views are same, namely that they have zero disparity. For a dual pixel image pair that exhibits defocus blur, the disparity occurs in the defocus region of the two views. Specifically, a px is horizontally displaced between the two views. It suggests that the defocus kernel of the dual pixel camera is horizontal symmetric, while the kernel shape and size are dependent to the blurriness or disparity. Here is a toy example of image formulation in the dual pixel camera. Therefore, in our disparity over deblur module, we first define a candidate set of horizontal symmetric kernels. In each region of the dual pixel image pair, the disparity suffered is used to carry the candidate kernel set for combining into kernels. That best describes the blur suffered in the image region. The combined kernels are inverse to deblur kernels, and then are used to restore an all-in-focus image from the dual pixel image pair. Considering that the ground truth dual pixel disparity are absent for supervising the aforementioned process, therefore, we introduce a reblurring regularization module. Given an input in focus dual pixel image pair, you reuse the combined kernels for reblurring the sharp image into the defocus blurred central view of the dual pixel image pair, regularizing the learning of the candidate kernel set and kernel combining process. Meanwhile, we also note that features from sharp image regions are nearly preserved before and after our deblur module. They should have large similarity. This motivates us to design our sharp region preservation module. By comparing the similarity of feature map before and after deblur, we might in-focus sharp regions within the dual pixel images, and preserve features from these regions to improve the feature map quality for restoring the all-in-focus image. Here is an example of the similarity feature map we obtained for the dual pixel images. Our overall architecture is shown here. We compare with state-of-the-art methods on DPD blur, DDD Synatic, and RDPD dataset respectively. Here, we provide some quantitative comparisons of our method and the state-of-the-art methods. We further investigate our model components. Our method does not require ground truth disparity map for supervision. Then, how the nerd disparity feature look like? With obtained disparity feature from our model, we perform K-means algorithm to cluster similar disparity features across the image. The assigned cluster IDs are used to colorize the latent features in our model. The regions exhibit different amount of defocus blur are clustered separately. In the following, we investigate how the nerd curls look like in our model. We linearly transform the image space to feature space and train a live weight model for beta curl visualization. We visualize the subkernel with the largest weights assigned by the disparity features for different image regions in our model, showing some amount of correlation with the defocus blur suffered in the image. Here is a reference. Thank you for your listening and time. If you are interested in our work, please scan the QR code for more information.